All right, so let's go ahead and get started for today's lecture. So far we've talked a lot about what limits are, and now we're going to talk about technically an application of the limit, if you want to word it that way. In particular, we're going to talk about what is continuity, what does it mean to be continuous, what does it mean to not be continuous. So even though it's already on the board already, whenever I say the word continuous or not continuous, what comes to mind for y'all? Would be an example of something maybe in a drawing that's not continuous? It's something that ends. And in particular, if I want to be very specific about being continuous, imagine that I'm drawing a line on the board. Well, you don't really have to imagine, I can do it right here. Let's say I'm drawing a line, and then I never lift up my pencil. This would be an example of something that is continuous the entire way through. But if instead I had to pick up my pencil at some point, that would be an example where I'm no longer continuous. I had to pick up, had to make a hard break in my drawing. So informally speaking, a continuous function, remember we can always graph a function, is a function that can be drawn on its domain without lifting your pencil. In other words, going from left to right, you can trace it without lifting your pencil. If you can do that, then we're going to call it continuous. So let's go ahead and we're going to jump straight into our first example here. Here I gave you a graph, and I have it on the intervals from 0 to 4. As a reminder, whenever I have this interval, 0 to 4 with parentheses, that means everything in between 0 and 4, but I'm not really looking at 0 and 4 itself. Those round parentheses means I'm not including the end. So I'm not including 0, I'm not including 4. So if I give you this graph, tell me the point where I am not continuous. And you can just give me the x values for it. So at what x values? Let's see, I heard 1, I heard 2, I heard 4. So let me go ahead and write that down first. 1, 2, 4. Let's go ahead and check all of them and see if this is correct. All right, so using my informal definition, let's start on the left. I'm going to quite literally trace my graph. So on the left, I start here. And then if I want to keep on going, I have to lift up my pen and go there. So that tells me I am not continuous at 1. So yeah, I agree with 1. Going over, continuing to trace, I get to this point, x equal to 2. I have to lift my pencil, hit the dot, and then continue forth. So at 2, I am not continuous. So yeah, I agree with 2. Keep on going. 3, I can keep on going without lifting my pencil. And then 4, I have to lift my pencil and then hit the 4. But I'm going to go ahead and actually erase 4. But why did I erase 4? I agree, I had to lift my pencil, but why did I not include it? Yeah, it's at the end. Remember I said that this is the interval only from 0 to 4, not including 0, not including 4. So that's just a very small nuance thing. Yeah, I did pick up my pencil, but I told you right here through this interval, I don't care about 0, I don't care about 4, regardless of if it was continuous or not. All right, so really we just had 2 values for x for which I am not continuous. So we're pretty much done here. Highlight this? I guess not. I guess it's only text. All right, so if I give you a picture, you can tell me very quickly if we're continuous or not. Each time you lift your pencil, not continuous. Any questions for this first example? All right, so now let's go ahead and look at example 2. Example 2, determine the values for which this function, h of x is equal to, it's a little small, x squared minus x minus 2 over x minus 2 is not continuous. In other words, if I were to graph this, when would I have to lift my pencil? For what x value? What's a way I can interpret this if I just have the function here? What would be an example of when I'm not continuous? Any ideas on what might I even do to approach this problem? Yeah, so if I look at this function, first off, it's a rational function, meaning I have some essentially a polynomial on the top and on the bottom. There's a certain number here that gives me undefined. What is that number that makes this function undefined? 2. Because if I plug in 2 on the bottom, I get 2 minus 2. I get 0 on the bottom, which we know is undefined. So let me write that out. If I look at the denominator here, x minus 2. Well, when x minus 2 is 0, that's when my function is not defined. And if I'm not defined, that means pretty much if I would draw it, I would have to lift my pencil at that point. So here, if I solve for x, I add 2 to the left and right, and I get x is positive 2. There's something I'm leaving out about this. This is the final answer. But there's something else I want to mention about this example. So here I have h of x, which was, I'll rewrite it, x squared minus x minus 2 over x minus 2. So what I want to mention about this is you're probably noticing I could factor this if I wanted to. This is not going to affect our final answer that we already talked about. On the top, this does factor into x minus 2. Let's see, and then let's say x plus 1, negative 2, add to negative 1 over x minus 2. And then you might think, well, I have x minus 2 on the top and the bottom. I have x plus 1. Despite this, why does this not change anything for us? The fact that I still have x equal to 2 as my value. Why is this not changing anything at all for me? I believe it's something I mentioned in a previous lecture also. It's still not continuous, but why? Even, you might think, well, this can be simplified down to x plus 1. I got rid of the thing on the bottom that was causing the issue. But how come that doesn't do anything for me? Even though the x minus 2 is gone, I still claim that I'm not continuous here. So if you recall from one time, I agree, these two are equal no matter what. You can plug in any number that you want, and these are the same. But what about what I have? What I have here? See if I can clean that up a little bit. X plus 1. If I look at this on the right and what I have on the left, are these always equal to each other? No, remember, yes, these are equal almost everywhere, except for one value, which is x equal to 2. And this tells us a little bit also about why it's not continuous. If I just gave you this alone, then we're continuous everywhere. But if I give you this, we're not continuous at x equal to 2. Because also that these are not the same everywhere. There's one number, x equal to 2, where these are different. Because here on the left is not defined. You get 0 over 0. On the right, you would get 3. Clearly, 3 and undefined are different things that we're looking at. So this was just a warning saying if you're ever looking for where I'm not continuous, all I'm worried about is from the beginning, what's my denominator? When is it 0? I'm not going to try to simplify it or anything like that. All right, so any questions about this example 1 or example 2? All right, so for this definition of continuity, It relied pretty heavily on the fact that we could draw a graph, or I can figure out exactly where was it not defined. And that uses a very informal definition of continuity. So how does this relate to what we know about limits, and can we formalize this a little bit better? So let's go ahead and move down into this definition here. How do I know when something is continuous for sure? Using a limit. So if I have a function, let's call it f. A function f is continuous at the number a if the following occurs. The limit as x goes to a of the function is equal to f of a. How can we interpret that visually? Well, remember, the limit is what number are we approaching? That's what's on the left. On the right, that's the number we are actually at, the y value we're actually being defined for. So basically, if the y value that I'm approaching is matching where I actually am, that tells me I am continuous. There's not a mismatch from where I am and where I'm heading. And if I want to do this step by step, and another equivalent way that you can interpret this is that we can say that f is continuous if all three of these things apply. My function is defined. Because if my function is not defined, I can't be continuous. 2, the limit exists. That means if I look to the left and right, I still have my function. And then 3 would be checking that same rule. Is f of a equal to the limit as x goes to a? So I call this the continuity checklist. And this continuity checklist says that if any one of those conditions fail, then we are not continuous or discontinuous at a. Or you might hear me say f has a discontinuity at the number a. So this is how we're checking for continuity. I'll give y'all some time to copy this down. All right, so we now have a definition or a way to check if my function was continuous at some x value. So if I gave you a function and I said, let's check, is my function continuous at x equal to 2? Then you would check all these conditions for x equal to 2. Another thing that we can do to really get this down on this 3-part checklist, if I were to draw you a picture of a graph, let's just say it was like this. Is this graph continuous, yes or no, at that point? No, because clearly I can try to trace it and then I have to pick up my pencil to trace it. Let's relate it to what we have on this checklist. Is my function defined? Let me go ahead and draw this a little bit more. So we have it. Pull this a right here. So is my function defined at x equal to a? Can I say figure out where it is? Well, in this case, I am defined. It's this dot right here. Because remember, defined means if I plug in A, do I get a number? In other words, can I find a point there? So in this case, I am defined. Does my limit exist? Yeah, I can look on the left, trace my graph, look on the right, trace my graph. My limit would be whatever this number is here. So the limit does exist. Is f of a and my limit the same number? No. Again, this is f of a. This is my limit. So this are not the same. So then that shows that this is not continuous a little bit more formally, rather than saying, can I trace it? Again, if one of these fails, then they actually all end up, the whole thing falls apart. All right, let's go ahead and go into example 3 now. Determine if the following function, g of x, is continuous when a is equal to 11. Again, I'll give y'all some time to copy this down so that y'all can listen as needed. So I have this function, and based on what x is equal, I'll use either the top expression or the bottom expression. Because remember, whenever I give you a function like g of x, usually we'd be like, all right, what's g of 5? And that would mean x is equal to 5. And then that'll tell you, do I use the top or the bottom expression? So to check if we are continuous at this point, or this value, a is equal to 11, I'm just going to go down my checklist. I'm going to check, am I defined? Does the limit exist? And is the limit equal to where I'm defined, what I'm defined as? So we're doing our checklist. So the first part of the checklist was f of a is defined. Is defined. So what's my a value for this problem? 11, right? It says it right there, a is equal to 11. So really what I'm asking is if f of a is defined is, can you tell me what f of 11 is? Yeah, we'll get 9. How'd you know that it was 9? Yeah, so remember, whenever I say f of 11, it's saying x is equal to 11. What happens whenever x is equal to 11? It says our answer is 9. So this is 9. That is defined, we got a number answer. So the first condition, that's fine. I don't see a problem yet. Second condition, can I find the limit? Limit as x goes to 11. So if I take the limit as x goes to 11, what is this? I should have used g to be exact, since I said g here. Just use that so we're consistent. The limit of g of x. So whenever I take a look at the limit as x goes to 11, usually we have the limit of some function expression. So let me write this. Hold on. Stop going in and out. The limit as x goes to 11 So I know that g is either one of these two expressions. If I'm taking the limit, which expression am I using? This top one or the bottom if I'm taking the limit? Yeah, we're going to use the top one because whenever we talk about the limit, we're saying as x approaches 11. We don't necessarily say as the limit when x is 11. We're saying whenever we're close to 11. Well, if we're close to 11, then I'm using this top one. I'm not equal to 11. I'm just really close to it. So if I want, I can fill this in and say that really we're taking the limit of the top expression, x squared minus 121 over x minus 11. And now it becomes a problem. Do we know or remember how to evaluate this limit? What's the first thing I could probably do? Let's see, how do I evaluate this limit? What's the first thing we usually try to do? Yeah, we try to see if we can plug it in. Am I allowed to plug in 11? Yeah, we can try to plug in 11, but yeah. Yeah, we can go ahead and factor this. I can't plug in 11 because clearly 11 minus 11, I get 0 on the bottom. That's a problem. So I can try to factor this. And fortunately for us, this does in fact factor. What's the top factor into? Yes, x plus 11 minus 11. And then on the bottom, there's nothing that changes. All right, so that's great. We have x minus 11 on the bottom, and on the top, we get some cancellation. Someone tell me what the final answer for this part is, the limit of this expression. Yeah, we get x plus 11, the limit of x plus 11. What can I do from there? Yeah, we can plug in 11 because we got rid of the thing that was giving me a 0 on the bottom. That was the big issue. Now that that's gone, I can go ahead and try to plug in 11 once more. For lack of space, I'm not going to write this over again. We get 11 plus 11, giving me 22. So part B, 2, the limit does exist. That's great. My last condition for continuity. Is it true that F11, is this equal to 22? So is it true that f of 11, is this equal to the limit? I keep on using f instead of g, that's my bad. G of 11, is this equal to the limit of g of x? In other words, from what I got from parts 1 and 2, are those the same number? Nope, I can definitely say that 9 is not equal to 22. 99% sure. So unfortunately, this is not true. That means I failed one of the conditions for continuity. If I fail one condition, then I fail the entire thing. Yes, so that means my function g is not continuous at a is equal to 11. So like we can say something like no, or you can say discontinuous. Discontinuous. I'd much rather take it zooming in sometimes than the other one. Discontinuous at x equal to 11. Or we can say a equal to 11 because we're just using a and x as placeholders. So we're discontinuous, going through all of the steps for checking continuity. Any questions about what I did for this example 3? We just went down the list and checked each one individually. So this was really nice looking at this function because it was saying we had one thing if we're not equal to, if x is not 11, and one thing if x is equal to 11. As sort of a quick recap thing, does anyone know what type of function this is called? Starts with a P. Polynomial. It does involve polynomials. A function where there are different parts to it. Starts with a P, 2 syllables. It's in pieces. So this type of function is actually called a piecewise function because it's pieces. We have different pieces of the function depending on what x is equal to. All right, so we have example 3. So this worked out whenever I was defined, whenever I want to be not continuous. Move up. Looks like it froze. This is reacting. Let's go back real quick. See if I can get that to reset. While this is doing that, I can still talk about stuff. So this was continuity, and it involved our regular limit, the two-sided limit. So the next thing that we'll end up talking about once this reloads is, okay, so I have a two-handed limit. Can I do anything with my one-sided limit, the left hand and the right-handed limit? So can anyone give me a guess about probably what we're gonna do before we use the two-handed limit, and that was for continuity. So if I use the left-handed limit, then that's going to be referring to what we're going to call left continuity or left-handed continuity. What do you think it's going to be called if we use the right-hand limit? Yeah, right-handed continuity. I'll decide to do that. Pull it back up. Going back down. So you don't really have to write this definition because it's the same thing as continuity, but with the left hand and the right-handed limit. There we go, finally. So let A be a real number. Remember that fancy notation? A looks like a backwards E with a double R. That just says A is a real number. Be in the domain of a function f. The function is continuous at C if we have the limit is equal to the actual value. This is what we've been doing so far. And I see a little bit of a typo here. This should be at A. Make all these C's into an A so that we're consistent. And then we're right continuous, or you say continuous from the right, if the right-hand limit is equal to my actual defined value. Left continuous, or you can say continuous from the left, if the left-handed limit is equal to f of A. So we have these three types of continuity. But why would I care about being left continuous and right continuous? Well, remember that first example, we had endpoints. I can't do continuity for the endpoints, but I definitely can do left or right continuity for the endpoints. Because remember, I had a graph. If I have a graph that looks like this, I don't know, and this is all I have, can I really find the two-handed limit at this point? No, because there's not even a left side for me to look at. Same thing over here. I can't really do the two-handed limit because there's no right side. And I know a limit, I look at the left and the right. So instead, for these endpoints or stuff like this, we can actually go ahead and talk about the left and the right hand continuity. All right, so this is the definition. So using that definition, well, before we go into the example, do y'all remember that one theorem about the left limit and the right limit versus the two-handed limit? What happens whenever the left and the right hand limit are the same? What happens to the regular limit? Yeah, it's the same number, right? What happens if the left and the right are different? Yeah, and then the limit didn't exist, right? So here, since we're using still the left, right, and two-handed limit, if I am a left continuous and a right continuous, that means I'm continuous. It's continuous is kind of like two-handed continuous. The same thing in the opposite direction. If I'm continuous, that means my limit exists. For my limit to exist, the left and the right hand limits have to be the same. All right, so now let's go ahead and look at example 4. Here I've got a function, and I want to check, are we continuous at a is equal to 1? Or also, can I check if I'm right continuous, left continuous? Or I'll use this word in air quotes, completely discontinuous. And now I have the piecewise function k of x is equal to x plus 3 if I plug in a number smaller than 1. Or it's equal to x squared minus 5x if I plug in any numbers greater than or equal to 1. All right, so for all of these, we are still going to use the same checklist. What was the first thing on my checklist to check for? Yeah, we check if it's defined at that point. In other words, in this case, does k of 1 exist? So that's exactly what we'll do. So for part 1, does k of 1 exist? So for k of 1, which one of these functions am I using, the top one or the bottom one? Yeah, we're going to use the bottom one because, again, k of 1 says, what is k when x is equal to 1? Well, this function, this piecewise function tells me if x is equal to 1, I use the bottom function. So in other words, k of 1, I'm plugging 1 into the bottom. So I get what? 1 squared minus 5 times 1. 1 squared, I get 1. 5 times 1, I get 5. So this is 1 minus 5, or negative 4. So in other words, when I plug in a is equal to 1, I got a defined answer. First one is done. Now I have to go ahead and check for the limit. But I can't automatically get the two-handed limit anymore like last time. Because if I look at this piecewise function, when x is less than 1, is that to the left or is that to the right of 1 for the top? If you're smaller than 1? Yeah, you would be to the left. Smaller than 1 means that quite literally on the number line, you are to the left. So to find a two-handed limit, one thing I can do is find the left-hand limit first. Because to get the two-handed limit, I can find the left and find the right, and that's going to tell me everything I need. So for part 2, let's find the left-handed limit first. The limit as x goes to 1 from the left. as x goes to 1 from the left. Remember that little minus symbol means from the left of k of x. And y'all already told me, well, y'all didn't tell me, I kind of already alluded to this. Which one of these functions am I using for the left-hand limit, the top one or the bottom one? The top one, because again, we said when x is smaller than 1, that means to the left of 1. Since I'm working with the left-hand limit, I should work with this one up here. All right, so what is this going to be equal to? Yeah, again, if I can plug in my number, then we can go ahead and do that. We get 1 plus 3, we get 4. Do I need to find the right-hand limit now? Why not? Yes, perfect. So I could find the right-handed limit if I wanted to, but I know it's not going to matter. Because if the right-handed limit is 4, then the two-handed limit is 4, but that's still not going to be equal to negative 4. If I find the right-handed limit and it's a different number, then my two-handed limit doesn't exist. I fail that condition. So regardless on what the two-handed limit is, the right-hand limit is, it's not going to give me negative 4 in the long run. So in other words, I know I'm not continuous. Either I'm going to fail condition 2, my limit's not going to exist, or if it does exist, it's not going to be negative 4. So I'm going to fail either condition 2 or 3. It doesn't really matter. As long as one of them for sure fails, I can say, what can I make about my conclusion? Am I continuous at a is equal to 1? Yeah, so if I look at this, I can go ahead and automatically wipe out continuous. I can actually also wipe out left continuous also. Why can I wipe out left continuous? Yeah, we found the left-hand limit, and that's not the same as the original. What about right continuous? Do y'all think I'll be right continuous? Yes or no? Just looking at it. So looking at this, I'm going to think that we're going to be right continuous. And here's why. For right continuous, I check the right-hand limit, right? Right-hand limit, would I use the top or the bottom? Yeah, I would use the bottom. I could still plug in 1. What I would get, 1 minus 5, I would get negative 4. So I'm not going to show it on here, but it will turn out that we are, in fact, right continuous. If I found the right-hand limit, it is going to turn out to be negative 4. There was also another big hint that was telling me that I was probably going to be right continuous. Can anyone tell me, without even looking, before we even did the limits, what was probably a big hint that I was going to be right continuous if I just gave you the problem? If I look at this right here, this said when x is greater than or equal to 1. That tells me if I were to graph this, whatever it might look like, on the right end, right of 1. So if I had a graph, whatever it might look like, let's say that right here is 1. That means since I have a greater than or equal to sign here, that means from the right, I know I would have a closed dot in some line. So since I know that I will have a closed dot because it's x equal to 1 here. That means from the right, I know I will be continuous. In other words, this little equal sign right here was a very big key indicator that I was going to be right continuous. Now, I still have to check for two-handed continuity one way or another, but then that's a quick way that I can check for right or left continuous. If I had this instead, what if instead I had greater than, and then this was less than or equal to? Do you think I would be right continuous or left continuous or what? Like, let's say that this one did not have the equal sign, this one on top. It would be left continuous. So this is a pretty big indicator for at least this type of function. You can imagine that, yes, there are more complicated scenarios and nuances, but for examples like this, that will be a very big indicator. All right, so we know that this function in particular is right continuous. Any questions about this example 4? All right, so next thing I will talk about is, so far we've been doing continuity at a point. Next thing I'll talk about is continuity on an interval. In other words, instead of one point, a range of numbers. And this one will actually be a very quick one for us to cover. A function is continuous on an interval, that range of numbers, if it's continuous for every single point in there. And then for the endpoints, I would have to check for left and right in continuity. And we're actually going to do 3 very quick examples where I determine the interval of continuity. So if I look at this one, for example, looking at example 5, let's say I wanted the interval of continuity for the function m, defined by m of x is equal to the square root of 4 minus x squared. And let's actually make this one a problem a little bit nicer to avoid confusion. Let's erase that. Let me erase one thing. Let's do it 4 minus x instead of x squared. So the question we would have here is, how do I even start looking at interval of continuity? I'll give you some time to copy stuff down before I continue. If you've already finished writing, you can start thinking, how can I even think about the interval of continuity for number 5? What was my first rule on that continuity checklist? Yeah, basically that it was defined at that point. So maybe the first thing I want to do is figure out, when is this function not defined? So whenever I'm talking about a square root, when do I end up with a problem of being defined or not defined? Yeah, so if I think about square roots, one of the first things you learned about square roots is that we didn't want to take the square root of a negative number. So in other words, whatever I plug into that function, I want to make sure that I don't get the square root of a negative number. In other words, what's underneath the square root for this one? Yeah, we got 4 minus x. So for this to be defined, I need that 4 minus x needs to be greater than 0. But I can also put greater than or equal to 0, because I can still do square root of 0. That's not a problem. If 4 minus x is negative, then I'm taking the square root of a negative, and then we have a problem. We're not defined, at least for the real numbers. We're not going to be talking about imaginary numbers. All right, so here at 4 minus x is greater than or equal to 0 because I do not want to take the square root of a negative. Can you solve for x for me here? Well, I can do that by, let's say I can add x to the left and right, for example. If I do that, I get 4 is greater than or equal to x, right? I can add x to the left and to the right, and I have this. And if you're more comfortable with it, you could write this. We're used to seeing x on the left. X has to be less than or equal than 4. Just because we're typically used to seeing x on the left instead of the right. So can you tell me what this looks like in interval notation? Anyone remember interval notation stuff? So we'll do a very short review of interval notation. Whenever I look at this, this is negative, x is less than or equal than 4. Or if you think about it, this is 4, and are these the numbers to the left of 4 or to the right? If I want to be smaller than 4. Yeah, to the left of 4. So as it turns out, if I want to write this as an interval, then this would be the number 4, and then every number to the left. Every number to the left, that would go all the way to negative infinity. Other rules about intervals, infinities for us always have parentheses. And I'm going to go ahead and put a bracket on 4. Does anyone remember or know why I put a bracket? It's an endpoint, but more precisely, why? Why not a parentheses? Yeah, right here we have x less than or equal to 4. That little equal sign tells me I should put a bracket on the 4. If there was no equal sign here, then I would use a parentheses, because this tells me I include 4 in my interval. All right, so I claim that this right here is my interval of continuity. I'll talk very quickly about why. Am I defined for all numbers in that interval, every number smaller than 4? Can you plug in anything smaller than 4 and get an answer? Yeah, for sure. I did not break rule 1. Rule 2, well, if I can always draw it that way, that means I should be able to draw it without ever lifting my pencil. If you want, just for a visual, this graph looks something along the lines of this, if I remember right. Something like that, if I'm thinking about this correctly, very quickly in my head. All right, and then at this end point, I'm actually, do you think I am left or right continuous at this point? Yeah, and why am I left continuous? Yeah, because we're drawing from the left. All right, so there's a lot more I would want to talk about this, but we are out of time for today. But the long story short is that if you have a square root, we're going to take whatever's inside that square root and say it has to be greater than or equal to 0, because we can't take the square root of a negative number. And because this calculus class is a calculus of real numbers, not a calculus of complex numbers. All right, so that's all for today.